So it's really a pleasure to be giving my first ever talk to the physics group. I've given a talk to the maths group, but that doesn't count again. So, okay. So I'm going to talk about how some Lie algebras potentially arise from counting Dyonic degeneracies. And first, there's an apology I would like to give. I mean, there is no physics motivation for this problem. It's just some mathematics which is being driven by inputs from physics, and which is the Dyonic degeneracy problem. And this is some work I've done with my student Shabir, who just defended his doctoral thesis. He's in the postdoc market. And Vishwanath, who is a mathematician who works on Lie algebras. And our long-term goal is to write at least one mathematics paper based on this work. But the work I'm reporting is extremely preliminary, and it's appeared in 2 of these papers, which are already in the archive. And so the plan of the talk is there'll be an elaborate introduction, and then after a practical introduction to superalgebras, or not superalgebras, actually Lie algebras, the super part will be downplayed, but it can be put in. And the crux of our work is an embedding of an affine SL2 hat into a particular family of Lie algebras. And from that, we get some vector-valued modular forms. And there's a beautiful theory of vector-valued modular forms, which we use. But again, I cannot get into all the details. You can look at it in the paper, or, of course, you can always ask questions. And then how to go beyond VVF. And then I'll conclude. OK, so the surprising thing is that the generating function of the degeneracy of quarter BPS or 1/4 BPS dyons in n equal to 4 supersymmetric string theories is a genus-2 Siegel modular form. So this Z here, the Z here is, you should think of it as the period matrix of some genus-2 surface. And the charges, so there's a vector of charges. And so QE and QM are the electric and magnetic charge vectors, and you define what are called T duality invariants. And so there are 3 integers. N need not be integer, it could be fractional, but just N, L, and M, they are some combinations of the charges. And so this is the degeneracy. And the surprise is that the counting function in this is a Siegel modular form. And so the first example was done by Dijkgraaf, Verlinde, and Verlinde, and it was pretty much after Schrödinger-Vafa. And in some sense, this was the second example, but this was a 4-dimensional example where we were able to match this degeneracy for large charges with that of the black hole area by 4 formula. Okay, so in these theories, there is, so this phi k, so remember the inverse of this is what appears here, but I'll focus on phi k here. Sometimes if you take a square root, you can always take a square root, but what you want is to get objects which have integral Fourier expansions, integral coefficients. And so in some situations, the square root works, and you get a new Siegel modular form of half the weight. And there is a very interesting connection with the denominator formula of some Lie algebra. And the idea here is that this formula is something which you should remember. Delta is some automorphic form. It could be a Siegel modular form. Pi is some product formula, and sigma is some summation formula. Okay, so the details of pi and sigma will be related to the Lie algebra. So this is the kind of connection that one is looking at. Okay, so in all the nice examples that we will get, we can extract something called a Cartan matrix. Okay, I'll explain this in detail. So this is just supposed to be, so given a Cartan matrix, there is a standard construction which gives you a Lie algebra called a Kac-Moody Lie algebra, and it's just called G of A. And then there is a particular extension due to Borcherds, which leads to a bigger algebra, which has a nice connection with a Siegel, with some automorphic form. Okay, so you have this chain, Cartan matrix, Kac-Moody Lie algebra, then you get a BKM Lie algebra, and then you get an automorphic form. And so that delta, so this delta will have a pi and a sigma. Okay. That is something which we will see. I'll even give examples. Okay. This is just to give you the picture. So he does add some things to it. What is added, we'll know. But in 3 examples, we know A, kind of, we know G of A, but we don't know if there exists an extension. It's conjectural or whatever. I mean, the idea is there an extension? But we know it's not of this variety. And this is something which we prove explicitly. But what physics gives us is modular form, delta, which always has a pi expansion, and a little bit of the work is in trying to understand the sigma part of the story. The pi part is known. Okay, so this is the kind of setup that we have. And you may wonder, there are only 3 examples. Yeah. It's a Kac-Moody algebra. Okay. So if for particular, I mean, so it depends on the matrix A. So if you take A to be 2 minus 2 minus 2, 2, then that would be the SL2, affine SLSU2 at level 1.
Sorry, Suresh, sorry.
Yeah.
Can you just repeat what is pi and sigma again?
Yeah. It's just a picture. It's just, and it's worth going back. Somewhere I had it. Yeah. So what I'm saying is that this delta is an automorphic form, and the Lie algebra story is that you can write it as a product formula and a sigma, and the devil is of course in the details, but this caricature is very important. That's all. Okay. So what I'm going to discuss is, we'll discuss 2 families of Siegel modular forms, and I'll give you the context a little later. But so the first family consists of 5 Siegel modular forms. There is a lot of details out here. So delta is the same delta which I mentioned, but it's K. So there's a series which n equal to 1, 2, 3, 4, and 6, no 5. Okay. And U is that it appears, this is something which is related to umbral moonshine, and so-called A series of umbral moonshine, and the weight is given by some formula. That's not so important. But these are Siegel modular forms, not of the standard SP4Z, but some kind of scaled version of it. So it is, so these are called paramodular groups. So if you put n equal to 1 here, this will become a normal symplectic group in 2-dimensional or 4-dimensional phase space. Okay, so that's what happens. But this is some embroidery on this, which depends on n. But this group is not some subgroup of gamma n and gamma 1, where gamma 1 is our normal thing. They are not subgroups of each other. Of course, you can construct intersection and you can get something, but this is like a full group. And so again, you can go ahead.
So what does it? This is in Q, right? Not Z.
Yeah, it's in Q. Because there is an n inverse here.
So then when you say it's a multiple of n, then the numerator.
Yeah, which has to be integer time. So all stars are integers. So these stars are integers.
So there's only that entry which is.
This is the offending entry. Yeah. Absolutely. Okay. So you can you take this variable z, and it can be written as a 2x2 matrix, and I just call them tau and tau prime and z. These are my variables. The off-diagonal guy is z. And so you can take a limit which is like tau prime goes to I infinity or s goes to 0. You get an expansion as a power series in S. And this n comes up here. Usual, if n equal to 1, for every power of S, so there's a half shift. Don't worry about that. After a half, there will be a 3/2, 5/2, etc. But here what you get is something which is shifting by powers of n. Okay. And this is related to the fact that this n is appearing out here. Okay. So you get, what you get is as the coefficients of S, I mean, it's a function of tau and z, and this is a Jacobi form of weight k and substitutable index. Okay. So all you have to remember is that if you take this and take the S equal to 0 infinity, you get an infinite series of Jacobi forms. And if you've ever looked at how the transformation of Jacobi forms, there is an ugly phase, etc. But if you think of it as arising from in this thing and put suitable powers of S and let S transform, you'll find all those ugly phases go away. Okay, so in some sense, Jacobi form should carry this S factor to get rid of all the ugly phases. And it's also very natural in affine Kac-Moody algebras, where you have to extend your Cartan by adding an extra generator. Okay. So what you get, so the first guy would be m equal to 0, and let's just call that phi k half. So that's an index half object, and k is the same as this k. Okay, and that has a very simple form. It is theta 1, the Jacobi theta function, times some power of eta. Okay, now the next guy in this, which is, if you put m equal to 1, it will be phi k n plus half. And that guy, you can take this as a definition of psi 0 n. Okay, and this is just the same phi k half which here. So if you pull out, so out of this, the first two terms give us phi k half and psi 0 n. So just so that you can remember, just remember that there were two objects which we extracted from this. Okay, and if you know a little bit Umbral Moonshine, these are also Jacobi forms of index 0, but sorry, weight 0 and index n. These are the Jacobi forms which appear, which have the nice expansion, and you see characters of various finite groups, finite simple groups come. Okay, the second family is much more simple. It appears in CHL orbifolds of heterotic on T6 or type 2 on K3 cross T2, and this n here is just it's just the Zn of the orbifolding, but the k prime of n is not a nice formula, so I can write it for prime n, etc. But I thought there are only, again, 2 to 6. There is n equal to 1, but that's already there in the previous case, so it has some particular weights. I just written it out explicitly. And these are now modular forms now of sp4z, but rather some level n subgroup of gamma 1, which is sp4z. And now if you look at the same Jacobi expansion, which is take s going to 0, the first term will be, of course, 5k prime half. It's exactly like before, but now you will have from you will have terms, Jacobi forms from index 1, 2, 3, so forth after you pull out this term. So, and we will focus on the first n terms. In some ways, the first family is simple because between 0 and between 1 and n, and between there's a skipping in terms of n, and in some ways those are the simplest examples. It's kind of counterintuitive, but it is a simpler example. This is much more messier, and but there are, so we will focus for for reasons which I won't explain now. That at least we have to go up to s power n. Okay, so these are all Jacobi forms of gamma 0 n with some character.
M equals to n term here is not the same as that.
No, it's not. But there should be, the statement is that there will be something, some parts of it which should be the same. That's why we need to go to. Yeah. So we have 10 Siegel modular forms, 5 from each family. And so the proposition is that these are denominator formulae. Again, I'll explain all these things for some suitable extensions of Kac-Moody algebra. So for this n, which is common, there's an n which I used for the CHL, there's 2, 3, 4, 5, 6. And for the other one, it is 1, 2 to 6, skipping 5. Okay, so they all, so what we will see is that we can associate for each of these a Cartan matrix. From that Cartan matrix, we can construct Kac-Moody algebra. So up to that point, there is nothing great. But from that, there must be some extension such that you get a connection with delta. So this is the proposition. And so for the first family, for n equal to 1, 2, 3, and 4, this actually is old work of Gritsenko and Nikulin. These are standard examples. Okay, and these are known to be Borcherds extensions of GAN. So in the second family, there is reasonable evidence. Reasonable in the sense that we physics audience will say it is reasonable because we have checked it to some order. So we refers to people like Cheng and Dabolkar, then me and my student Gopalakrishna. We all sat down and we have done some checks, but we haven't really sat down and proved it. But there is no doubt in our mind that there exists. And we are actually trying to give a proof which will be, eventually write a proof which would make use of our methods. So, but that's work in progress. So in the fact, so there's reasonable evidence for n equal to 2, 3, and 4. But now the open cases, n equal to 5 and 6 in CHL or the second family, and the n equal to 6, which is still there in the thing. So there are three examples which are not for which it's not Borcherds extension. And in this talk, I'll tell you what is not, at least. Okay.
Examples are
one from family 1, 2 from, yeah.
and this AN is, you say rank?
They're all rank 3 matrices.
All
There are only 6 of them. I will see what those are. Okay. They're all rank 3, but they could be bigger. So they're degenerate, except for n equal to 1. Okay. So there is some work of Gritsenko and Nikulin which says that if such a Lie algebra exists for these 5 and 6 cases, then it cannot be a Borcherds extension. Okay. So that's a no-go theorem. So this concludes the introductory part of my talk, and now I will try to give you more details about some of the things. I don't think I'll do justice to everything. So we'll start with root lattices from wall crossing. So if you look at quarter BPS states in n equal to 4 string theory, there is something very nice which is not there in n equal to 2 of the kind you have studied, which is that it's enough to focus on single-centered, and if you think of them as black holes, and 2-centered black holes. Because 3-centered and higher, they're like very low co-dimension. So if you're crossing walls, so there will be walls of marginal stability where 2-centered might decay into 1 center, or the other way around, they could form bound states. So the question is, what are these walls? And somebody in the audience worked out those walls. That's Ashok Sen. And so squares of these modular forms, I mean, we took the square roots, so I'm going backwards now. So I'm just using some slightly different notation out here. I'm taking care of fractionality. So it's the same thing which we wrote. So, but now the degeneracy of dions jumps, as one crosses walls of marginal stability where 2-centered BPS objects decay or bind depending on which direction you're going. And every wall is characterized by a pair of rational numbers, B over A and D over C, with AD minus BC equal to 1 and B equal to C equal to 0 mod n for n less than or equal to 4. For n 5 and 6, you have to go away from this. These characterize moduli dependent curves in the dilaton axion upper half plane, which begin and end at these points. And in special cases, the walls are arcs of circles. So here, the first one is to look is this is a hyperbolic upper half plane. So these two will meet at infinity. So you have the first one is a hyperbolic triangle with 3 parts. When you go to n equal to 2, this is kind of modded out in some sense, and you get some new thing. So you get, and each wall is associated with some simple root. So we can even do counting. So you can see that this thing will be, has 3 simple roots. The next one has 1, 2, 3, 4. Next one has 6. Okay. And once you know these intercepts, you can actually work out what the what can you work out? Yeah, you get the roots. There's a formula which I will probably flash next. Okay. 4 onwards, something interesting happens. You find that you have infinite roots, first thing. And so you start, so you do this process, and there is a limit point which is half. Okay. And so you can show that these circles, there are infinite of them, and the limit point, they end up with the limit point half. And similarly from this side you come, and so you at the end of it, so you can see that you get infinite roots. Okay. So there's already A4 onwards, is you're not dealing with finite number of simple real roots. And for 5 and 6, something weird happens. The limit point, that is, you can follow the process which Ashok did, and then you find that you get a limit point which is irrational, and it sort of terminates, and there's a symmetry about half here. So same thing happens on the other side, And so then what you do is you start from half and you try to look for walls and you get these sort of blue roots. Okay. And the thing is that if you think of, so you get these, so from the walls, we get a map to what are potentially roots of some Lie algebra. That's the map, again, which I'll show you. But 5 and 6 are already weird. Okay, so from walls to simple roots, here's what happens. So Cheng and Verdillet observed that the walls that appear in n equal to 1 are the walls of the Weyl chambers of the BKM Lie superalgebra. This was a known algebra, like I said, studied by Gritsenko and Nikulin. And so this was the map which Ashok did. So these are the intercepts, B over A and D over C. From that, you get a root which is alpha, which is a symmetric 2 by 2 matrix. But this can be also thought of as a vector in hyperbolic space, R21. That's a simple map which takes you from this to this a 3-dimensional vector into a 2 by 2 symmetric matrix with a Lorentzian norm written in this way as -2 times determinator. Okay, it's easy to check that the 3 vectors alpha 1, alpha 2, alpha 3 have norm 2. That means the determinant is -2. I labeled them, but I didn't discuss it. So let me just show you somewhere. So alpha 1 and alpha 2 are common to all of them. Alpha 3 will change. So it's like the one going from 0 by 1 to 1 by n. Okay, alpha 3, for instance. Similarly, you will have alpha naught, which goes the other way. And there are many, many more roots, but we'll just focus on 2, 3 of them. Okay. So, and the same map actually goes through for walls which are not just n equal to 1, n greater than 1. And this is work of Cheng and Borcherds, and then me and my students. And then one defines a Cartan matrix as the gram matrix or the inner product of these roots. And all Cartan matrices have rank 3. Okay, so 1 second. I thought I would have some pictures, but okay. So first thing is, so like I said, each of these roots, you can think of them as some vectors in Minkowski space, R2, 1 or whatever. Right? And then you can construct lattices out of these guys. So you get some Lorentzian lattice with these as the basis vectors. So you could have infinite of them, but remember that they are linearly independent in some sense because you're only allowed integer combinations. So even though, so you get a lattice which looks like this, all integer things of this vector in some rank 3 Lorentzian lattice. And these lattices have a special property. They admit something called a Weyl vector. And so this Weyl vector for every n, it has this inner product. For all I, even if it's infinite, it gives -1. Okay, and rho n takes this form. So Nikulin, he has classified such lattices, Lorentzian lattices with Weyl vector. So 3-dimensional Lorentzian lattices, and they fall into 3 types depending on the norm of this rho vector. Okay, it's elliptic if rho in our convention is norm convention is less than 0. Parabolic if it's equal to 0, and hyperbolic if rho is greater than 0. So what we find is that for n equal to 3, 1, 2, and 3, this rho is of elliptic type. N equal to 4 is exactly, if you remember, this was proportional determinant. You can check that this will have determinant 0. So that's of parabolic type. And the n equal to 5 and 6 cases are hyperbolic type. Okay, so now I can repeat the theorem of Gritsenko and Nikulin, which says that there are no BKM Lie superalgebras for case 3. And Nikulin did a lot more. Actually, they were classified all the lattices. So there are, it's not like there are 3 examples. He has some 60 plus, I don't know the exact number, some 60 odd examples of that. Okay. So now I will just connect up a little bit. So I call this a periodic table of root lattices and Siegel modular forms. And so we have 2 things out here. So this is for people who know So this n here is with respect to, you take the heterotic case and you do CHL orbifolds, you can go up n to 1. I mean, there is 7 and 8 also, but we stop it. The square root doesn't work in those cases. So 1, 2, 3, 4, and 6. And M is the twining story. So you can have twisted twining indices. And so what you find is that if you go along this, you're changing the value of M. But what that does is it never changes the real roots, the Cartan matrix for all. So with A1, there are many different extensions in some sense. You take GA1 and you can construct for every one of these guys, there is a distinct Lie algebra. Okay. Similarly for A2, there are all these examples and this thing, so on and so forth. But this is special. So one more thing I said, this is these guys I said are related to Umbrel Moonshine, but they actually appeared in my work where I was looking at twisted twining Siegel modular forms, and I noticed that these were the same things which Tritsenko and Nikulin. So they appear in Dion counting, refined Dion counting. 4 of the examples appear, but this doesn't appear. But so the 4x4 part I had worked out long ago, but then with my student Samuel Sutapa, we worked the rest of these guys. There are more, but I'm just putting a few. But this one does not fit any Dion counting problem. But if it's just some natural thing that there is one more candidate which appears, if you just think of these guys as Umbrel Moonshine story, you get one more where the square root works, and there is a product formula, so on and so forth. So this is something which we don't have a physics intuition, but we have a candidate, but we can prove that it has this A6 guy. Okay, so we have and the blue is the CHL orbifolds 2, 3, 4, and 5. So all these guys we have, what we have are nice product formulas, and to some extent we put in some work, and we have actually some, not I would say great formulae, but some closed formulae for not closed, but we have a formulae for the sum side as well. They're just giving them names, just distinct. Yeah. Okay. So the in the 4x4 part, this Q and Nablas, these were Gritsenko and Clary's. They defined and he requested that I use his notation, so I have stuck to that.
So this is for a lattice. It's a notation that.
So no, this is for a modular form. These are all these. Yeah.
The notation that you have in each entry, it is for modular.
It's for the modular form. So if I come, let's look at this. Delta tilde 3. There is a sense in which these two are different cusps of the same thing. Delta tilde 3, the weight is 3 here. And then there is a cycle shape, etc. I've just put, there's a lot more information than I'm describing. So what we have is Cartan matrix and its associated. So this will tell you about the root lattice. This will tell you this is the modular form. And what is written out here is a concrete object. Okay. So this table kind of captures it, but we are just focusing on just 2 such things. Okay. But that's good enough because it covers the exceptional cases. Okay. No, so the Grassmann, so we are looking at only the we are looking at the real roots, the bosonic part of the story. There is a fermionic part we know some things about that. Yeah. Yeah. So the thing is they have some conditions. They have some conditions.
Super matters.
Yeah, super matters there also. Yeah.
Crucial in the sense that superalgebra only for one signature, the opposite signature that
No. Superalgebra is just there are fermionic roots.
There is no it's not like there's some positivity constraint.
No.
But why is it that only?
So no, the point here is that we are focusing on the real simple roots. That's all. Nothing more. But what happens is that in the Borcherds extension, you add. You actually find that you will be adding fermionic things, but you don't add real guys. That's the condition.
Even without adding in the previous slide, you had no superalgebra like this.
Yeah, I mean, in some sense, ordinary algebra is a subset of. So it's a stronger statement. It's a stronger statement. Yeah. Okay. So the Cartan matrices, you can write them out explicitly, and yeah. Yeah, it is. I have the figure somewhere. I think it's after this. I have lost the pictures, I think. Sorry. I thought I had the. Oh, that was there, right? So one more thing I should mention here is that these blue roots are something weird. So when I talk of A, it's just the red roots. I don't talk about. I mean, we look at these guys, but.
So my question is that some of these roots are with walls of is ratio 0, 1, they're using one root alpha.
Yeah, correct.
But you had a figure where some of the roots were affiliated to the transition. Yeah.
No, there wasn't any like that.
Yeah, so alpha 3 is what is that? How should I understand alpha 3?
Alpha 3 is with the intercept 0 by 1, 1 by 4. Yeah, this is going to the other thing is infinity, which you should write as what 1 by 0. 1 by 0. Okay. Yeah. So one feature you can observe here is that if you take a 2 by 2 subspace of anywhere, it's always 2 minus 2 minus 2. Okay, it's even though here there's a nice beautiful formula, but again, it's infinite, so I cannot write something very simple. Okay, so but the whole point here is that if you notice that there is also a cyclic symmetry, you look at the next guy, it's shifted by 1. Okay, so there is actually a huge dihedral symmetry. It's not just reflection. So there's an enhanced Weyl group, which is the Weyl groups, which is a Weyl reflections, and these dihedral symmetries. So if you look here, if you just focus on this, it tells you that there is a SL2 hat sitting inside that. Okay. And you can write a nice universal formula in terms of some quantity called lambda, which is where lambda is any root. There is symmetry if you look. So lambda is some root of this quadratic equation. This form was written by Gopalakrishna, which is very nice. Okay. So how am I doing with regard to time? Okay. Yeah. So this is not a talk on moonshine, but maybe I'll say a few words on umbral moonshine. Okay. So umbral moonshine is a generalization of Mathia moonshine. Mathia moonshine, what was Mathia moonshine? It took this group, a sporadic simple group called M24, and what we got from that was many objects potentially, but so we got eta products. We got Jacobi forms, we got Siegel modular forms, we also got Mach modular forms. Okay, so what happens is that if you look at the Fourier coefficients of those guys, the dimensions of, or sums of dimensions of the irreducible representations of that group appear mysteriously. Okay, so that's the moonshine story. And so Harvey, Cheng, Duncan, and Harvey, so they wanted to extend, so they looked at there's a finite list of Mach modular forms of a particular type, and they started out, let's ask, can we write something analogous to that? And they got a whole bunch of groups. So for instance, the first next one was M12.2. So that's also at least a sporadic simple group, but after that, they're very artificial groups, but they fit into a beautiful story in which is extending Mathia moonshine, and it's actually a fairly extensive thing, and it's intimidating to read their papers because each of them is like 150, but lots of tables, of course, 200 pages, but it's a beautiful thing. The final story is that associated to every Niemeyer lattice, there are 24 of them, they have a story. Okay, so A1 power 24 is where Mathia moonshine would come. A2 power 12 is the other example which I said. So for the A series, they have given a Jacobi form of weight 0, that is the analog of the elliptic genus of K3. Okay. And what we did is use this Jacobi form as a seed, and there's a product formula that we can write. So we constructed a Siegel modular form using a multiplicative lift due to Clarion grid synchro. Okay, we get a nice Siegel modular form and square root. So we can do it for all the A series. There are more than the examples that I showed, but the square root doesn't work for the other examples, so it stops at 6. The 5 modular forms, the first family that we are considering, are the only ones for which the square root leads to things with integer coefficients. Okay. Okay, so here I will, I just want to set notation a little bit, nothing more. And so that, so we know that we have this sort of decomposition into the Cartan and positive and negative roots. Any Lie algebra, just for, like you have for SU2, J plus, J minus, and J3. And so the analogous thing you can do for any Cartan matrix, you give me, so you get, we can have some simple roots, we call them E alpha 1. I goes from 1 to R, and they provide a basis for R plus. And the Lie algebra in the Chevalier basis can be written, and this is where you find the Cartan matrix can appear. Okay, and then there are some surrelations. The takeaway from this whole thing is a Kac-Moody algebra. You can write the full Lie algebra, which I'm not showing. If you give me this data A, J, I, even give me the Cartan matrix, you can write it. Okay, so if the Cartan matrix has zero norm, you have to handle things. If it has negative norm, all these issues can be done, and so you can construct a Kac. So this is the structure in which you construct Kac-Moody algebras. I'm just giving you, I think, a caricature of that. So the takeaway here is that you give me a Cartan matrix. That's a standard construction, and which will give you a Lie algebra, and that's what I call G of A.
This does not involve the zero.
Yeah. So you know, you can extend. So you would extend the good point. So if you take, so the Cartan may have to be extended if invertibility is an issue. So yeah, you keep relaxing rather. It's mostly free. I mean, in all our examples, I assume they are symmetric. Okay, but even there's something called symmetrizable. You can relax even that condition. So, but I'm just taking. Okay, so so the point is that if you give me any root, there's a reflection you can do, and the Weyl group is just generated by taking all the reflections of the real roots. And this is not changed even if you have fermionic roots. Okay, though Serganova discusses fermionic reflections, etc. But in our setup, we don't use that. Okay, and so the Weyl vector, usually in standard examples which we see of finite simple semi-simple Lie algebras, it's just half of the sum of the positive roots. But that property, that's not the nicest way. So one defines it in this fashion, and you can check that in those cases also this is true. And this minus sign has to do with a convention which Gritsenko and Nikulin follow, and I follow it because people, if they want to match with them, they don't have to worry about signs. Okay, sorry about that. So the Weyl-Kac denominator formula has the following structure. The sum side is a sum over. So we saw the Weyl group, it's a group. So so this doesn't matter if they are infinite or whatever, it is just sum over the full Weyl group. And this is just some sign of the Weyl this thing, and with Weyl group acting on this. So this gives you the sum side. And you can see the Weyl vector up here. Again, it's conventional. Sometimes people put it here, but there's a reason I put it here, because it matches the story of the modular form story. Okay, so my convention is to put it here, times the product formula. Now the product formula knows all about the positive roots. So you can see that the structure, so this knows about the simple roots, simple real roots. This knows about all the positive roots as well as the Weyl vector. But the open question, if you give me some G of A, the hard question is to compute multiplicity I told you in a nice way, you give me a Cartan matrix, I'll write for you this whole thing. But I cannot tell you what the surrelations which have to be imposed can be very messy, and it's not, it's a problem of research in some sense, if you're given something to work out what the multiplicities are. So it's pretty hard job. Okay. But for affine Kac-Moody algebras, the answer is known by connecting the multiplicities. These are connected to Jacobi forms. So this is the first real appearance of the use of modularity, and so the multiplicity problem is solved for those things because of the connection with Jacobi forms. Okay. And I should tell you why it's called the denominator formula, I guess. So there's something called the Weyl-character formula. So it's in some sense the calling card of every representation is a character. And so the Weyl-character formula has a numerator and a denominator. And so the denominator is, that's why it's called the denominator formula. But if you take the trivial representation, you get sigma equal to pi. So the numerator should be equal. So the trivial representation is character should be 1. So that can be rewritten as sigma equal to pi. Okay. So I always enjoy working with examples. For me, mathematics doesn't stick if I don't have examples. So you take this as a standard SU3 Cartan matrix, and the Weyl group is S3 here. It has 6 elements. So if you write the summation, you will get 6 terms. And it has exactly 3 roots, alpha 1, alpha 2, and alpha 1 plus alpha 2. So relations imply there are no more. So it's a very easy case, you write. So you get a product of 3 terms, all with multiplicity 1. And if you go ahead and expand it, so naively you would have thought there are 8 terms, but there's a cancellation. So you get 6. So it's very easy to check. Let's take this 2 minus 2 minus 2. And now what you find is delta. So this is, if you look at the determinant of this, it is 0. So this delta, which is alpha 1 plus alpha 2, is 0 norm. So in the Lie algebra story, first thing is norm is actually what we in physics will call norm square. And if norm is 0 or negative, norm square rather, is 0 or negative, it's called imaginary root. So delta is an imaginary root, but it's not simple. It has 0 norm. And so what happens is if you just try to, so you get large now, you can define your positive roots this way, but you find that you're forced to include in your set of positive roots m delta, where m is some greater than 0. So that gives you the product side, giving you all each appears with multiplicity 1. Okay. Then you make some identifications. E power alpha 1 is this, e power minus alpha 2 is R inverse, and e power delta is Q. Okay. Then what you do, if you ask what is, so pi becomes this. Okay. And don't worry about this factor, it's important, but what is relevant here is if you have seen the theta 1, the triple product identity is precisely that. And now theta 1 is a known object, and remember I mentioned to you, it has weight half, index half. So you multiply it by s power half, it has nice transformations. Okay, so it's not conventional to put s power half, but I am putting it. And what about the sum side? Sum side turns out to be exactly, again, what happens in all the affine cases is that you can write it as an infinite, the Weyl group of the affine as a semi-direct product of translations with the Weyl group of the underlying group, finite simple group. So it always becomes a, so in this case, you get this, if you look here, there's a minus 1 power L. So that it'll be a sum of, you can write it as sum, it's a difference of 2 terms. And you can see that's the Z2 of SU2. Okay, so you get this, and so this is again a well-known, but it's a non-trivial identity here. It's not something. And actually this was the first use, and it was done by MacDonald, who pointed out that the product side has to be modified. He turned this around and looked at it from the viewpoint of Lie algebras and said, hey, look, we need to put that in to make this work. Some side you can write, but if it has to equal Jacobi product identity, tells you, please do this. I already solved the problem, so because it's known, but that was the contribution.
We realized that we need to add
M deltas. They're not simple, but okay. Yeah.
W is an element of the Y.
Yeah. Yeah, yeah. Oh, I mean, it's you can associate. Every reflection is odd. So any while element can be written as a combination of them. So it's how many of them that. So minus power this thing. It's yeah, you can call it sine of W, some standard determinant. Yeah.
So this multiplicity of alpha, you're saying that how long it takes for the same relation?
No, it says yeah, multiplicity. It says how many independent. I mean, how many? You give me one weight alpha, or you give me a root. It's a non-simple alpha. How many ways you can get it? You don't. There could be.
So that's a question of how many.
Yeah.
For the same relations to terminate.
Yeah. So the multiple. Yeah, you have to work. So this is not something. Yeah, you need some work. Multiple base, all these things. So.
And so the statement is that has something to do with geometry.
For affine. For affine.
So, but in this affine case, the while group also has this translation.
Yeah. So the yeah, exactly. So that's why it's always sum. So if you take the affine SU3, right? It's underlying SU3 is 8. So not A. So it's S4, right? Yes. Yeah. So you will get so many infinite sums. You will get with signs, etc. Yeah.
So the level doesn't.
These are level 1.
All level.
They are easier ones. Yeah.
Because the translation is in units of K or K plus.
Yeah, it's more complicated for higher level. This is level 1. Yeah, good point. Okay. So now comes the thing. If you give me some general G of A, nobody. I mean, the answer is sort of there are Katz-Petersen have some formulae which put bounds on the multiplicities, etc. And then people have written computer programs for certain examples and computed to fairly high levels. A lot of sophisticated things, but there's no closed formula of any kind. But Borcherds did something interesting. He says, so far we have not had simple roots which are imaginary, that have 0 or negative norm. So he said, let's add them into the story. How many should I add? Okay, that is the question. So his idea was you keep adding it until that object which you have becomes some automorphic form. Okay, of course that's not the way you do it. You construct an automorphic form and then interpret that as multiplicities, etc. Okay, so that's what. So you construct some object which looks like this, and you solve the multiplicity problem. Okay, but now the price you're paying is that you're adding roots which have 0 norm or negative norm. They're simple. The delta we saw, which had 0 norm, was not simple. It was just alpha 1 plus alpha 2. Okay, so now what he needs to do is to, but the Weyl group is still the Weyl group of the usual stuff of this thing. So you have to do some modification. So we just call this modification T. He has some definition for it. Okay, so he needs to modify. Bottom line is that he needs to modify the sum side. Okay, to make it work. Okay, so at the end of the day, you get something, and this is where remember I told you if you give me A1, there were like some 5 or 6 examples. They all differ in what kind of imaginary simple roots you have added. That is the difference.
Is it guaranteed that with these alphas it will satisfy all this?
Oh yes. Oh yes, yeah. Yes. Oh, that is one of my goals, to understand his proof properly so I can use it. So yes.
If you do any completion,
he eventually writes for you. So you add this root. So now you have an enhanced Cartan matrix extra. He writes the full algebra also. What it is? He called it a generalized Kac-Moody algebra, but now we all call it Borcherds-Kac-Moody algebra. So yeah. It's a theorem. He's after all a mathematician. You have to look at his methods are not that. So he Yeah, he turns it the other way. So in fact, many cases, the product for it's called the Borcherds product formula. He invented the method in some sense to do that. So
Starts with the right hand side.
and then go to this side, and then yeah, absolutely, yeah. It's like
The only statement is that we can try to even assignment. It is define an algebra posing itself.
yeah.
The only question is whether they are consistent.
I think they'll be considered. It'll be. I mean, it's like G of A exists.
If the set relations are okay.
You know, I mean, yeah, you have to impose it. It's a relation, and there is no contradiction.
The only question is that whether you can come up with some alphas, come up with some T for any modular form or any other one.
No, that and so yeah. So that's the issue is that for many modular forms, you can write a product formula, but you can't write a sum side. Sum sides are very rare. So yeah, you're right. It's not guaranteed that if you give me a product formula, that there exists. Yeah, that's not guaranteed.
To have a product formula, you can always write there sum.
Yeah, but you need more structure. There is more structure. That's absolutely. I agree with you. But I mean, it has to have this structure, at least this structure. Yeah, there exists. I'm not saying that doesn't exist. It's some sign. It's some sign, plus or minus 1.
So is he having finite number of metrics?
No, it's infinite.
Different number of
Yeah.
which have an infinite number of.
Yeah. We'll see an example soon. No, how many terms? How many is like if you're taking it's a sum of odd number of or even number of simple roots, imaginary roots. Okay, so yeah.
So to get the sum side, we know that we have to modify it, but there's modification something.
No. His proof is much more cohomological kind of. No, much more. Anyway, you'll see. Yeah, you'll see the next example. At least answer for that example what it is. Okay. So here's the case. So we start with theta 1. We saw was 2 minus 2. This was SL2 hat. So to that we are going to add. Delta. You remember was we'll add same weight as the previous delta, but these are now simple. So we'll add m copies of delta, 2 delta each of these guys. Okay, and then the relevant Jacobi form is just a product with eta of tau power m. Okay, so now you go back the product side. You can easily write. You just eta as a simple thing. This part will get modified. You can see this. That's needed, by the way. And so you get this is the modification. The product side is there. And then you can work out what is the correction term. It's really kind of simple in the sense that it is just this. You don't expand this. You keep this as product in some trivial sense. And this is the terms. So you have a concrete. So this is the Borcherds correction term. I've written as q power p. Borcherds correction term should be e power p delta minus p delta in my notation. So here is the simplest example of which I call B SL2 hat m. Of course, you can take not just this, there can be eta products. In fact, for the case of CHL, it's not so simple. Okay. So all the Siegel modular forms which I wrote there, they have certain nice properties. And this is where modularity is important. How do you prove something? What you do is you have a Weyl transfer, you take an elementary Weyl reflection, and if you're able to convert it into action of the modular group, then you know what is happening. So under elementary Weyl reflections, you expect it to change sign. And so you embed this action. So I've written it, it's SI acting, it should be acting on the roots, but you can translate it as acting on Z on the period matrix, and then you get this. Okay. So that's what you get. For n equal to 5 and 6, the additional roots, those were the blue roots, they do not generate any symmetries. I just call them, there's a mapping between the two sets. For every alpha I, there is an alpha tilde. Okay. All of them.
Somewhat W was still somewhat W.
Yeah. It's only whatever would have been in G of. You're just adding extra terms due to the imaginary simple roots. They modify.
And I think that there is on the some side we don't add.
Yeah. No. But you can prove the dihedral symmetry also can be proved that way, because we show that you can embed it again. I'm not discussing the dihedral group here.
The sum side W is not W. Doesn't have the dihedral.
This one is no. Dihedral is an independent symmetry, and but you can prove that it is invariant, not sign, and the dihedral shift. Okay, this is the modular form is also in. Okay, it's some work, but you can prove.
Is it because you're writing it as some sum over some sums? Should I understand this T part as coming from the dihedral?
No. That dihedral symmetry will map simple roots to real roots to real roots. It doesn't change norm, nothing. So it will again, it can have some action on the imaginary simples, but it has nothing to do. So in fact, what I'm saying is that these deltas have the exact properties that you would expect of a denominator formula, and that you prove it through modularity. So that is a nice part. Which one?
The T addition of T in the last line. What is the object? Argument of, I mean,
so T would so if it's a Borcherds correction, so we know. So the point. Let me just finish. So all of them admit product formula in at least two ways: product implied by generalized moonshine, and a product formula due to Clarion-Gritsenko. It was a big headache because these two, they didn't seem to this thing. And I remember being in 2012 or something completely confused. Even my referee asked me some questions, and I said it must match, etc. And there was some idea missing, but then it's a little bit complicated, the relationship. So in some cases we are able to show, but eventually, at least for twining genera, Sutapa and I now have a complete story where we show that moonshine and the formulae, both product formulae are equivalent in some ways. Okay. So now comes the sum side. So if it were, here is the point. Let's assume it's a Borcherds correction. Then you wish to determine what this T is. Okay, and ask is it coming from imaginary simple roots, or are there some terms which don't even fit what Borcherds is saying? This is the question. Okay. So for n equal to 5, we also we want to determine which doesn't fit. Also, what are these alpha tilde roots? Those blue roots, do they play any role? Okay. So our goal originally was to, best thing would be, you have the Weyl group, write every term that you see in terms of the orbits, Weyl orbits, and then you're done. Okay. And the problem there is that groups are infinite dimensional, and I assure you, it's not for lack of effort. We don't have nice presentations. For the affine, it was beautiful. You could write it as some translations, semi-direct with the Weyl group of the finite subgroup. Okay. So it sort of started from half and we started to complete. Wall crossing only. It's all the Cartan matrices, etc. Everything is from physics.
But this last modular form is
yours. Yeah. So there it was extra work we had to prove. So we prove. Yeah. I'll discuss that in more detail. Yeah.
Log of x minus root t, is that a weight? Is that some of weight?
What?
Do I understand the argument?
Oh, this is just some formal way of writing it. No, it just has, if it says e power a, e power b equal to e power a plus b, addition of roots, etc. So w, it's just, if you have w of e power minus rho t, you can act as e power w of rho, w of t, something like this. That's all it means. It's short form. It's just short form for while acting on each of these things.
The example you showed, that t was just the sum over numbers times.
Yeah, which is e power p delta.
So this will be
minus
rho plus p delta.
Yeah. Okay. So, but now, so this was our idea and starting point after we kept going back and forth. I mean, whole of COVID was spent, I mean, shutdown was spent where we tried very hard to figure out things. But we figured out at least one thing, which was that there is an affine, this thing. But not just that, I told you we could always pull out some Jacobi form, the leading guy, and we wrote. Okay, so this guy, we can interpret this as a denominator formula for a particular Borcherds extension for SL2 hat. And it is true for each of all the examples, not just the guys which I'm looking. This is true. Oh, infinite. I think you can do infinite. Infinite. At least.
Down to the end, but I presume you can do other things also.
Yeah.
You can multiply
other things also. So it's infinite. No such thing. No such thing from this viewpoint. In fact, m will be -1 in one example. Okay. Okay, good. So this is actually a nice observation that this is even though it's ours, it's a nice observation. It tells you that there is this BSL2 hat, which is and SL2 hat, which is some subalgebra of whatever it is. That we know. Okay, so the idea here is to because there is SL2 hat, it's something which we understand, we have control. So the roadmap is the following: you embed SL2 hat into GAN. Okay, and this is done such that the Fourier-Jacobi expansion is compatible with the expansion in terms of SL2 hat. Remember, the Fourier-Jacobi was S tending to infinity. Okay, so that tells you that what it does is that you have to make some identifications, and it forces you to say alpha 1 and alpha 2, by enabling in the beginning those two common walls, those have to be your SL2 generators. Okay, and as he pointed out, the Cartan of SL2 hat as a third generator. So now that will go, and you can take either alpha 3 or alpha 0, and then you will get a 3 by 3 Cartan sub-Cartan matrix. And what you will find is that so you'll have H1, H2, H3. That's a 3-dimensional Cartan. You try to relate it to the Cartan of the extended Cartan of SL2. Okay, so the 3 also works out. So that puts some constraints, and some of you will know that the n equal to 4 superconformal algebra also as a SL2 hat symmetry. And I tried very hard to see if I could make this SL2 hat that, and it almost works, except there's a factor of 2, so they are not the same. Okay, so I spent a month or two trying all combinations, and it never worked. So we just said whatever we get is what we get. So this puts constraints, and then you expand each of these. So you saw the expansions. We got some size 0n's in terms of SL2 hat, and also we can do BSL2 hat characters. Okay, and the coefficients of the SL2 characters form a vector-valued modular form of SL2Z with weight 0 and known transformations under the modular group. Why is that? We know how size 0m transforms. We know how the SL2 hat characters transform. So its coefficients we can work out. Okay, so what we are doing here is that we want to know multiplicities of representation of SL2 hat, and that we are combining it into a vector-valued modular form. So the coefficients of the vector-valued modular forms will give you, we will let you track what are the weights of objects which are coming. Okay, so using the Q expansions to determine so Gannon had done some general work as follows. He says that if you give me a vector-valued modular form along with its S and T matrices, how they transform under tau goes to -1 over tau and tau goes to tau plus 1, okay, then he's able to, so he says that you can construct a basis for the modular forms of a given weight. In our case, always the weight is 0. And so then he writes this modular differential equation. The input for that, if the vector is r dimensional, extra data in addition to giving S and T is to determine one r by r matrix. Okay, so but we know only one solution. There might be r minus 1 other solution. So you need to do some guesswork, or you need to do some computer solution to that. And actually this, and there are other tricks which exist. So up to 4, you can actually go back and you can not just give your own, the modular forms, that weak vector valued modular forms, you can generate the full basis. Okay, so yeah. So he actually uses the J function, and it's actually, it's a nice Fuchsian differential equation with 0, 1 being the elliptic point and infinity being infinity. So he's able to, then you pull it back. Yeah, it's a beautiful piece of work. And so for up to n equal to 4 for the first family, that was our first, this thing we learned all about vector valued modular forms and solved it. And but for 6 we couldn't do it because the dimension was 7, and so you need to determine 49 elements. And again, I mean, failure is a common thread in this project, so that was one more failure. But for the second family, which is a CHL, you don't have at n, you have a whole bunch of guys. So for each one you have to do, and now the additional complication is that these are modular forms of gamma 0 n, vector valued modular forms of gamma 0 n. And so there is a procedure to convert. If you give me a vector valued modular form of n, you look at its orbits under the action, and you will get a bigger, much bigger vector, this thing which should fit. So you can see the size of the vectors start growing. It's out of control, and we really, up to 4 we can do, but notionally so we cannot solve it in that sense. So we really cannot, we just don't, it's not even worth determining the MDE in these examples.
Presumably now, not all of those solutions will be vector valued modular forms of gamma 0.
Which one?
If you take this big.
Oh, no, there is no, so let's go back to the first family. So there, so let's say we had rank 3. So he'll give 3, the family is also 3-dimensional. So you will get 3 different vector valued modular forms. But of them, one linear combination, or one, the way we do it, it's one of our bases. So your vector valued modular form, which is relevant for this problem, is the one. Okay, but it's interesting. What happens is that if you look at the CHL case, there when we went, we asked, we got some, one example, we got a vector valued modular form of this type, which was already there. And then I looked at what we got, and that turned out to be a linear combination of not just that thing. There were other, included one more other solution. Okay. Yeah.
Is there a statement that, let's say I give you n, gamma 0, like how big the vector value quantum?
Oh, yeah, easy. So you take you take the size of SL2Z divided by gamma 0 n.
So you just, for the statement it said
Times
the vector value modular form of gamma 0, and you want to take all its images.
Yes.
And put it all in the column.
Into a big vector,
So
yeah.
that it becomes a vector value modular form of
full SL2Z, yes. Yeah, this is a trick which Borcherds uses a lot. I mean, I just learned it, I implemented it.
So
it's,
yeah. This one, especially the statement is that, like, you can probably write down some modular differentiation.
Yeah. Yeah, but we don't know which one it is. We don't have enough.
And if you solve it, you will not end up with a solution which restricts to a gamma 0 n vector.
No, it will.
Let's say you kind of, let's say you have like some, let's say you have from 10. But all, like 10 element vector value model of SL2Z might not be the vector value model form you get caught by.
No, but if something is a vector value modular form of the SL2Z, it's definitely necessarily a vector value modular form of gamma 0 n. So, okay. Yeah, I know what you're saying, and actually something related happens. So when you take these images, what I find is that there's one combination which is actually ordinary modular form of the full group, and then it decouples, and then there is something else. So you get a split of 1 plus the rest.
Yeah, I guess what I'm asking is, if I give you a vector value modular form of SL,
that
you can always, I guess, just restrict it as it is.
Yeah.
Vector value modular form of gamma 0 n.
Correct.
But is there a way to restrict it to a smaller one? A smaller. When you say
Ah, good question. I think that is kind of guaranteed because of the modular properties which you have. I mean, the row representation knows that. So it is guaranteed. Yeah, good. I hadn't thought of it. It is guaranteed. Yeah.
Is there some diagonalization of S?
Yeah. So it'll be blocks. You will get the blocks. Yeah. I'll skip this.
There is no way to avoid this embedding in a set.
Okay. Here's the. I mean, no. This is something that's not true. One can, for at least some triangle groups, etc. So, for instance, gamma 02, gamma 03, and then there is also gamma 02 plus, gamma 03 or plus. There, so these are the genus 0 things where there's a different J function, and one has to redo the Gannon analysis. And so, at least for gamma 02 and 3, I think you don't. There's, I mean, this is like hammer to solve the problem. So, in those cases, I believe there is a new theory, but I haven't worked it out. In fact, I want to catch one of Gannon's students and ask him for a project to solve that.
Is it the point that you just want to find some J function? Like,
it's known. The J functions in the context of monstrous moonshine people have studied.
No. Or for any gamma 0 n,
Hmm.
you want to find something which directly allows you to write down the model.
Yeah, but you want what? There is a condition you need. Right? For it to go to the this thing, it should be there's a genus 0 condition. Not all gamma 0 n's fit that.
I understand.
Yeah.
But even for a generic gamma 0, I mean, what I'm saying is that is there a way to avoid accepting even for a generic gamma 0?
Yeah, I don't know.
Is that just a question of?
No, but I'm just thinking, right? I mean, yeah. If I can't give a J function, how do I? I mean, the way I think of it is you write it in the complex plane, which you get from the J, adding the point at infinity. Yeah. So.
But you didn't need the J function. I mean, if you have a notion of covariant derivative and gamma 0 and infinite modular forms. Suppose you have k dimensional vector.
Yeah.
You expect it to satisfy some order k differences.
Yes. Oh, you can. Yeah. We can do that.
And you write in terms of the gamma 0
and write the coefficient, which is what the usual. I mean, people who are doing bootstrap are doing. Yeah. Yes. We can do that.
That will be lower order difference.
It will be as much as the rank.
Yeah, as
the rank of. And you and yeah. So index of the group. So yeah, you're right. I mean, if I take something like if you give me gamma 0 n, I can do that. Each of them will be distinct solutions to. So from the viewpoint of if you think of it in terms of CFT, each of them is one of the characters of the thing. Of course, there could be multiplicity, number of distinct characters. Yeah, it could be that. That is true. Yeah. Okay, so I'll skip this and I will take probably 5 more minutes. Is that okay? 5, I think. Because these are examples we can see in some detail. So this is the denominator of the Borcherds extension of SL2. So this is the first non-trivial term. Of course, there are higher order terms. So this we already know. And for this, I can write it, m is equal to this. But you can see now, if I put m equal to 6, you'll see it is 12 minus 18 upon 6. So it's minus 1. So the imaginary, the root that you're adding is fermionic. Okay. And so the idea is to just go ahead and decompose this in terms we can do in both types of characters. So this is for size 0 n. So what you do is you get these. So now the tildes here represent characters of the Borcherds extension, and it's not. I mean, the relationship between chi tilde and chi is just some power of eta in some sense. Eta without the q power. So that's a standard formula. So you can expand it like this, and you get So for each things you get an n plus 1 dimensional vector. Okay. And the Q expansions you can work out. On a computer, it's very easy to do. But since we know a lot more about characters of SL2 hats, we prefer to do this. So instead of the Fs, we work with these Gs. And so you get these things which are vector valued modular forms of the full group. And we can work out what the modular transformations of these things are. So these I've already told you, but for n equal to 6, we couldn't do it, but we got the answer in a, accidentally we got this thing. We found that this can be written as a nice thing of some standard theta functions over eta. So this is just some standard theta functions. I'm not giving the definition. It's just standard. Okay. Second family is where it gets more intricate. So first thing is, so first set of terms you have to take n, and I'm stopping at s power n plus 1. So you get for every, even though I'm, so you can see that I will get n independent Jacobi forms of index going from 1 through n. Okay. And of course, this is for, I've written the formula for prime n. We know the formula for non-prime composite also. And that's, so these are also, there are some new Borcherds extensions which come, which you can see now it's not eta power something, but it's product, eta products come. Okay. Again, we can do the expansion, but now the expansion depends on which m we are doing. So you go, so we're looking at size 0m. So this size 0m, you can, it's similar to the expansion which we had for say where this m was equal to n. So there is some similarity between what we did for the case of the umbral moonshine examples, but so we get some different vector valued modular forms. Again, we work with the g's and we get this thing, and then I convert them into vector valued modular forms of SL2z. But now rank is like index of this thing times this one. Okay. So let's look at n equal to 2 umbral moonshine. So you get this f1, f2, f3. These are, this phi is just, I haven't defined it. It's just product of 1 minus q power n from n equal to 1 to infinity. Okay. So, and the vector valued modular form G has rank 3, and the first few terms are, so we have something like this. And we're able to solve for them. These are rank 3, and they are solved using 3f2. The hypergeometrics come. But for instance, if you take the next example, n equal to 3, it is rank 4, and there the answer is not hypergeometric, but we are able to solve for what the differential equation is, so we can write solutions. Now let's look at n equal to 2 CHL orbifold. So here the denominator for the Borcherds extension is theta 1 times eta over tau power 4, eta of tau by 2 power 4. And you get, so now there will be m equal to 1 and m equal to 2 sets of g's. This is rank 2, this is rank 3. Okay, all are modular forms of this thing. And now is where we start looking at things. So there's a 0 out here. If this were 1, this would be that root which got projected out in the n equal to 1 case. So that's important. This minus 4 is this 4. These are imaginary simple roots, and it comes with the sign is okay. It's one of these. It's the same 4. Okay. If you come here again, this one is so you have to go ahead and do some expansions, etc. This is one is coming from imaginary simple root, and this is the root alpha 3 as well as alpha 0. There is some symmetry in the problem. So you get, so these are things which you expect. So you can go and look for various terms. And the nice thing about this character expansion is that if you are focusing only on real roots and roots with 0 norm, they are very easy to track. They are the first few terms. So we are not particularly interested in the rest of them. So it helps you. So this character expansion is very useful in that sense. Okay. So let's look at the n equal to 6 umbral moonshine, and we will focus on roots with positive or 0 norm. Again, like I said, that means real or. So there are imaginary simples of 0 norm that appear, and delta, and this is actually, that fits into Borcherds correction. It could be fermionic, but it's a fermionic version of Borcherds correction. And the roots, tilde roots, alpha 1, oh, this should be tilde. Alpha 1 tilde, alpha tilde have norm 2. They appear with multiplicity -1. And these are supposed to be coming from super characters. So these are fermionic. So they do appear. Okay. So the fermionic roots seem to fit this pattern where it is some where you put 1 by e power minus alpha theta. So remember, these are positive norm and they are fermionic. Okay. And of course, we didn't check to very, very high order. I think we did one more term, but this is it. So this is not a deep check, but it is fitting this pattern. And let's go to the n equal to 5 and 6 CHL orbifolds. And so for instance, again, we can look at this delta. We know it's there are imaginary simple roots of this type, and there'll be fractional powers because there's 1 by n. So you get this T5. So for instance, so you find that the delta guys fit. We know what the expansions are also. So these kind of terms appear. So this is a standard Borcherds correction. Even for n equal to 5, there exist. We're able to show that. And okay, but the tilde roots alpha 1 and alpha 2, they appear on the product side, but on the sum side they don't appear. Okay, so they are not simple. However, what we do is we find new imaginary simple roots which have negative norm, and they have this thing which is 2 times rho n. Whatever reason, I don't know what that is. But they again have the same pattern as this. But unlike in this case, we have actually checked the first 5 terms in this expansion. So 1 minus x, so it's 1 plus x square, so on and so forth. So you check the first 5 terms, and then for some other reason, I needed to check that they don't appear, these don't appear, and we have to go to 10. So also check that the 10th term in this expansion. So it's fitting this, and it's true for both. So there is something uniform, and this is not something which fits. It's not a Borcherds correction. Okay. Now it would have been a Borcherds correction if beta at 0 norm, a fermionic root with 0 norm. But we know that these things have this you can check has non-zero. Okay, so it's very weird. It's like, so if you're doing say super algebras and you ask what is the rank 1 examples, there are exactly 2. One which is the the standard supersymmetry thing, BB dagger equal to 1. It's the SL2 to 1 or whatever it's called. There's some notation for that. It's one of those things. The other one is the OSP thing, which is the 0 mode of n equal to 2 SCA. So there's G plus square L0 you get from G. So that would have been, if it was that, then so that those have those. So the one of them has 0 norm. That is the usual fermionic Heisenberg-Weyl algebra. But it's not that. So it's like a very confusing situation where, so the Lie algebra interpretation is not at all clear. It doesn't fit. I mean, it looks like a simple thing. You give me one root, it just, and can we say something? I mean, it doesn't fit. And so this is our big puzzle. And there was one more thing which Dilip and Gopalakrishna we did many years ago, and there we were looking at you can get n equal to 4 theories by doing asymmetric CHL orbifolds of type 2 on T6, and for n equal to 1, 2, 3, 4, I think Ashok, Navamita, and Dilip, right? You guys did that. So there, for those examples, what we showed is that the analogous Siegel modular forms are ratios of what appear in the CHL case. And there also we found that there were roots of that. It was exactly this kind of roots we just did not understand. So one of the things at that time Dilip and I thought about it was, oh, maybe this is not a Lie algebra but a coset kind of thing. And that's still no problem. But what we would like to do is, at least at the very least, we should be able to write this whole thing as some representation over the G of A, at least that. Characterize that fully, and maybe even of Borcherds, all the things which we understand, and ask what it is. So at this point, what we have is, it's not like we got one beta, we have infinite of them because by symmetry. But if you think in terms of orbits, Weyl orbits, there is exactly one. This thing we haven't done the higher order things. And so yeah, so this is what I just mentioned that root beta has positive norm, then it usually means it's a OSP12. But we know the denominator of that, we know the denominator of this, and they don't agree. So yeah, I'll just finish here. So your next step would be to go and look at we stopped at S power n. What is the next set of terms? And nice thing is that moonshine gives you some beautiful formulae involving Hecke operators. And what this does is it tells you that if you know what is the beginning module for psi 0n, you can write the other guys by taking tensor products and doing some symmetric products and stuff like that. So there's a nice, and that carries over to the Lie algebra story. And so our hope is that we can use that to prove global, properties which involve everything. So that is still this thing. So what is this? Sorry, am I going backwards? No, what? I think I can skip this. No, I'll skip this. So I'll just conclude here. So is there a conclusion? There isn't one. Because we don't know the Lie algebra. Or we haven't answered the question. But the long version is we have some hope. And the Lie algebra interpretation is not clear. But then if such a Lie algebra exists, then it would be adding to the list of things. It would be some new kind of extension. And we know what that extension is, but we need what it means. Like somebody asked, we have to ask, can you write the Lie algebra for it? Write all the generators, what is the commutation relations or Lie brackets, etc. Okay. So what we have in mind is we are in the process of trying to complete the organization of all this thing. And are there more types of this beta type of roots? And is there anything special? Because all the ones which we have, they're always formulaic. So is there something special going on? And so that's all. Thank you.
Some questions for other.
Hello, can you hear me? Hello?
Can you hear me now?
Yes, thank you.
Yeah, go ahead.
Can you hear me? Can you hear me?
Yeah, I can.
Okay, thank you. Thank you so much for a very nice talk. I just want to make sure that I didn't miss something, because in the beginning of your talk, you had a table
Yes.
that had an entry along with a capital N and an entry with capital M.
Yeah.
And I would just like to go back to that just to make sure that I didn't miss anything. It was in the beginning of the talk.
I know.
Yes, that's it. Could you, because M sort of disappeared, and I was just wondering what is M's role, because N was obvious.
Yeah. So the thing is that these are what we call as twining. These are some refined counting which we do. So
Excuse me, I didn't catch
it's
that.
A refined counting.
Oh, I see.
Okay, so you refine by some symmetry, which is ZM.
So M is a ZM symmetry.
Yeah. So
and so that M doesn't play the role of, isn't labeled by little m in the final in there. No, it doesn't have anything to do with that.
Nothing. No, nothing.
No. And what does the crosses mean?
Crosses means those so you need, what you need is some symmetry, commuting symmetries of M23 or M24, something like that. So they don't exist. So those don't exist.
And it's understood why they don't exist?
Yeah.
Okay. So, thank you so much. Thank you.
Anything else?
Thank you. That was I just wanted to make sure that I understood that part at least.
Okay.
And since I'm on the subject, can you please recall what's the labels on this table? What is 124 and so forth?
Okay, so the thing is this: the square of these objects are related. At least these are related to Mathieu moonshine in some form.
Oh, I see.
So generalized moonshine involves two symmetries. So this NN there in that context is like order of symmetry N and M kind of thing. In the sense of Norton. And so what you find is that this 1 power 24, etc., are the conjugacy classes. So these are traces in the where you're putting you're doing in the conjugacy classes, where you're replacing the dimensions with the characters and in which conjugacy class.
I see.
These are all conjugacy classes of M24.
Thank you so much. Thank you.
Okay, you're welcome.